concave droplets transferred in the compartment of high-speed train. And Mr. Fushan is coming from the College of Mechanical and Vehicle Engineering from Hunan University in China. So, welcome.
Good morning, everyone. I'm honored to have opportunity to introduce some of my work. Oh. I'm honored to have opportunity to introduce some of my work in SUC 11. My presentation topic is numerical study of the effect of air supply relative humidity on cough droplet transport in the compartment of high-speed train. My presentation mainly includes 4 parts. The first is background, and before the background, I want to explain I can explain 3 words. The first is HST, it means high-speed train, and the second is ASRH, mean air supply relative humidity, and RH, it means relative humidity. Okay, as we know, the inhaling virus contain droplets is an important propagation route of COVID-19 or other respiratory infectious diseases. And the confined space is focused during the COVID-19 epidemic, and the typical confined room, including meeting room, classroom, high-speed train camp or high-speed train passenger compartment, bus. Compare the other confined space. The high-speed train has those characteristics. For example, high-speed train compartment is hermetic, and the high-speed train operating is wide. Those characteristics will accuse the air supply doing the compartment airflow and the ASRH virus with outside humidity. Therefore, the compartment relative humidity exhibit different conditions. And finally, the droplet evaporation rate may change. However, the effect of SRH variation on droplet separating high-speed train is not clear. And this study is helpful to epidemic prevention of high-speed train in different operating environments. And second is methodology. And the geometrical model is showing this finger. It's a high-speed train in service in China, and 19 mannequins arranged in the passenger compartment, and the infector, or we call the cough droplet realizer, located at the 9th position. It's the middle of the compartment. And with these 3 air supply relative humidity condition, RH0 and 15% and 95%, and we also see 3 droplet admission size, 20, 70, and 120 macro. And the Lagrangian method is used to couple the continuous fast and discrete fast, and the simulation software is fluent. The simulation city of the discrete fast and the continuous fast are also listed in 2 tabs. This study uses a fluent machine for computational domain discretization. The body, mouth, chair, bench, and the space near the mannequin are refined, and the total grid number is 14 minutes. Simultaneously, we generate a cross grid and fan grid for independence verification. Compare the velocity predict value of 3 grid. The middle grid and the fan grid predicts have a good consistency, and the middle grid is accepted to balance accuracy and the speed of simulation. The third is resultant discussion. The first, the airflow structure of compartment is domains the droplet movement. We take two sections to introduce the airflow structure, Z1, X1, where the Z1 represents the X direction velocity field. You can see in this picture, this picture, the airflow near the L has forward movement tree, and the airflow in the palm zone have backward movement tree. And for the X1, for the velocity field of X1, the offsetting sublet air flows meet and converge, forming a two-stable large vortex. And therefore, the airflow structure of compartment is stable, and the large vortex air near the L's and the palm may significantly affect the droplet movement. Okay, the next question is how the change of ASRH affects the follow field parameters in passenger compartment and the droplet evaporation process. For velocity field, we level the velocity measurement values at three different ASRH conditions. Obviously, for different ASRH, the velocity measurement values at the same location much well. And the second is a temperature field. We level the section X1 temperature field structure. Same as velocity, the variation of ASRH have little influence on temperature field. And third is relative humidity field. As we previously predict, there are significantly differences in humidity field of passenger compartment at different SRH conditions. And here we also summarize the compartment average RH and final for the change of evaporation characteristics. You can see based on evaporation curve and average evaporation time. In high ASRH, the evaporation time of 20 micro and 70 micro droplets are extended for each 95% condition. The 120 micro droplet can fall to ground before evaporation as neutral. So the droplet, it should be noticed that the droplet propagation and force characteristic may be changed when the ASRH varies. The droplet transport is the focus of our attention. Here, the three figure is the 20 droplet distribution result at 20 seconds. You can see the transport range and distribution at three ASRH conditions have good consistency. And for further quantitative explain, we also level the time varying number and the distribution and XYZ distribution at 0.5 seconds. Where the average distribution from the average value of droplet coordinate at each time. It represents the overall movement trend of droplet. Above all curve have a satisfactory consistency. So for 20 micro droplets, the change of ASRH will hardly help the change of their movement process. And distribution results of 70 micro droplets are shown in the three figure. And intuitively, there are few differences between RH0 and RH5%, and RH95% have few, and RH95% have fewer front row distribution like this, right? And the number of droplets represents the overall risk level in the passenger compartment. So first we show the clear rate of or time varying number. Through this curve, we can see the farthest clearance. We can see the RH19 12% have a farthest clearance rate after coding. And sedimentation is one of the important ways to remove the droplet. And so, second, we show the sedimentation number and trend. Through the two finger, we can we can see that the large number of RH95% fall to ground within 2 to 6 seconds, and for RH95%, more distribution near the ground and less distribution near the moles. So the RH95% condition have a highest sedimentation number and the strongest sedimentation trend. For the illustrate the movement direction of droplet, we also place the mean value of time varying distribution in x, y, z direction. The droplet movement character and select the key time to show the spatial distribution. The droplet movement characteristic of RH95% condition are also listed, and therefore through the curve we can see that the change of ASRH will change the propagation range of 17 microdroplet, and Henry SRH can reduce the infection rates. And the final is here the distribution result of 120 microdroplet at 20 seconds. And in most previous study, the droplet larger than 100 micro are usually considered difficult to suspend in space. However, for high-speed train environment or high-speed train compartment, there are still many 120 micro droplets separate widely at low ASRH. The time varying number also provides this viewpoint. Similarly, we also show the mean value of time varying distribution of 120 droplets in all directions through the curve for RH0 and RH15%. The remaining droplet in space are captured by the vortex again and moving passenger compartment for a long time. And in brief, the Henner air supply relative humidity and the largest number of droplets captured by the vortex. And the final is conclusions. This study we studied the effect of air supply relative humidity on droplet transport in high-speed train. The conclusion as followed. What's more, I think appropriately increasing SRH can help improve passenger compartment safety and during the academic period. Okay, thanks for your attention.
Thank you very much. Is there any question?
I've just two questions. So one question is about, because you're interested about high-speed train.
Yes.
But I didn't see anything in your presentation in terms of the setup reflected on the high-speed train compared to the normal trains. So what do you think is the high-speed train different compared to the other normal train?
Oh, okay. So the first. The characteristic of high-speed train. In normal train, the window will open, and for high-speed train, the compartment is hermetic, and the high-speed train opening is wide, and their compartment airflow are dominated by the air supply, and for normal train, it's may affected by outside wind or or outside the airflow in the compartment will disturb the droplet transport.
Okay. Have you done any kind of something like the air tightness? Because a normal train is still you can close the windows as well. So if you think about generalize your conclusions to the wider implications like a normal train, do you think it could be applicable to the other scenarios of the normal train, apart from open windows? Because a lot of the train you can still have air conditioning.
Mm,
Or it's only because the size is a majority is because all the ventilation systems are different, or how the supply inlet and outlet, the ventilation pattern are different for two types of the train.
we may focus the COVID-19 epidemic period. For example, in normal train in the epidemic period, we may they all open the window to increase increase air supply and to reduce the droplet time transporting compartment. And in this side, we make a difference between the high-speed train and normal train.
Because we have done that about 15 years ago about high-speed train, about infection disease transmission, the droplets in Hong Kong, about this similar study. And have you looking at validation? Because I didn't see any validation of your models there. You're looking at validation about the airflow patterns and also the droplet dispersions, the validation cases.
And this work mean focus the air supply humidity, relative humidity, and not other parameter, and in compartment the parameter including air supply velocity and air quantity,
Right.
and we also focus the air supply relative humidity because the ASRH varies with outside humidity. For example, the high-speed train driving in droughty or humidity environment, the ASRH may high or low.
Okay. Okay. Good. Thanks.
So I think because we have a little bit more time than other session, if there is any other question for the presenter, we have time for one or two other questions.
Or general questions that people are interested for the previous
Yeah,
presenter as well.
Yeah. I have just one on your study. I just want to know if you have identified any specific limitation from your study, something that may affect the result of the recommendation and so on. So something that people need to know before applying the recommendation. Have you identified any particular limitation that we mentioned?
Oh, can you repeat that again?
Yeah, I was wondering if in your study have you identified any particular limitation based on the assumption that you've done at the beginning of the design of the research that need to be, let's say, communicated when people want to apply your recommendation?
It's your limitation.
Limitation.
Yeah.
Limitation. Okay. In this work, the limitation includes in fact, the high-speed train is long marshalling, and 18 or 16 compartment combine the long high-speed train. And in this work, only a single compartment is considered. And in for the work, we may do some in long marshalling compartment, for example, two compartment or three compartment to research the air through the airflow through the compartment, different compartment. And the second limitation is the model of the discrete fast is mean the droplet model. We can improve we can consider the various activity to more accurate simulate the rates. Okay.
Thank you very much for
Thank you.
sharing. Any other question? Even for the presentation? If not, I think we're done. So
Yeah,
thank you
thank
again.
you. Thank you very much. And